Hey, want to know a secret right now? You can't know a particle's position and momentum with perfect accuracy at the same time. Not because our instruments are so dumb, but because of something called the Heisenberg Uncertainty Principle. In our everyday world, certainty feels natural. We can measure the speed of a car, the location of a planet, the weight of a rock, all with precision. But when we dive into the quantum realm, the subatomic world of particles, reality becomes slippery. And at the heart of that strangeness lies one of the most profound ideas in all of physics, the Heisenberg Uncertainty Principle. It's a rule that says the more precisely you know a particle's position, the less precisely you can know its momentum and vice versa. But before we get into the math, let me set the scene. In 1927, a young German physicist named Werner Heisenberg was working on the new, radical theory of quantum mechanics. The idea that the microscopic world of atoms and particles doesn't behave like the world we experience, but follows its own rules. And that's when he discovered something unsettling. The more precisely you know a particle's position, the less precisely you know its momentum, and vice versa. This wasn't a flaw in our tools, but a feature of nature itself. To understand this, imagine trying to measure the exact position of an electron, like one of these guys. To see it, you'd shine light on it. Photons, particles of light, carry momentum. The moment they hit the electron, they push it, changing its speed and direction. The act of observation disturbs what you're trying to measure. So the more precisely you try to pinpoint the electron's position, the more you disturb its momentum, and the less you know its position. You just can't know both accurately at the same time. And this isn't just for electrons, it's for any particle. The uncertainty principle isn't about fuzzy particles. It's about a fundamental limit in what the universe will let us know. Mathematically, it's expressed as the product of the uncertainties in position and momentum being greater than a tiny number, approximately 1/2 times Planck's constant. This constant, denoted by the letter h, shows up a lot in quantum mechanics. It's a tiny number, so small that when you're dealing with everyday objects, you never notice this limit. But for particles, it's a big deal. Before quantum theory, Newtonian physics had given us the impression of a clockwork universe. If you knew the position and velocity of every particle in the universe, you could, at least in theory, predict the future exactly. But Heisenberg's discovery shattered that dream. The universe, it turned out, wasn't a precise clock, but a sea of probabilities. So what does this mean exactly? Well, it means that if you're trying to figure out where an electron is, the best you can do is give a range of possible locations and a probability for each. That range and those probabilities will always be connected in a particular way, as described by the uncertainty principle. The electron doesn't have a perfectly defined position and momentum at the same time. The question, where exactly is it, may not even make sense until we actually measure it. And the act of measurement causes the electron to choose a definite location within that probability cloud. This is often described as the wave function collapsing, although what exactly that means is a whole other can of worms. Despite its counterintuitive implications, the uncertainty principle isn't just a theoretical curiosity. It has strange consequences which we can test and observe. It sets limits on how small things can be confined. It prevents electrons from spiraling into the nucleus of an atom. Without it, atoms wouldn't exist as we know them. It makes possible the quantum tunneling that powers the nuclear fusion in our sun. Basically, without uncertainty, you wouldn't be here. Today, the uncertainty principle shapes the cutting edge of science, from quantum computing to our understanding of black holes. It's a reminder that the universe isn't a machine of rigid determinism, but a dance of probabilities, where the question of what will happen is replaced by the question of what is likely to happen. It also reminds us that the act of measurement changes the thing measured, blurring the line between observer and observed. So the next time you reach out to grab that cup of coffee, Remember, you can't actually know where the cup will be until you look, thanks to the Heisenberg Uncertainty Principle. The universe doesn't reveal all its secrets easily. But that, as they say, is where the fun begins.